Johnny here with Simpson Math. In this video, we're going to uh, quickly talk about the sum difference identities, sine sum difference, cosine sum difference, tangent sum difference, and quickly I'll talk about maybe strategies to help memorize them or think about them. But then the focus of this video will be on using them. So let's just get started. So we just came from a video or lecture about deriving the sine sum identity, and that took a while. It took us drawing two angles, an alpha angle, a beta angle, showing them drawn together, creating a triangle, a bunch of different triangles with all these little perpendicular lines, then remembering some geometry facts about parallel lines and the transcendental, is that the word? And then the fact that the three angles of a triangle add up to 180 degrees. But it took a while. But we saw where maybe this one came from. So the rest of these may take a while as well. So we're not going to spend any more time on that. We're just going to put these in our notes and we're going to say these are true. These are the sum and difference identities, and we're just going to accept them as true to move on with some fun trig stuff. So put these in your notes, and there are some things we can maybe, like some patterns we can maybe look at to help us memorize them. So I remember that sine of two angles being added together. So sine of alpha plus beta is equal to the two trig functions, sine and cosine, plus cosine sine. So this is sine of the first, cosine of the second, plus cosine of the first, sine of the second. That's how I memorize the sine sum. Sine difference is the same thing. Sine of the first, cosine of the second, minus cosine of the first, sine of the second. Now I remembered in that order because of this minus sign. For the sum, it doesn't matter which one you put first. 2 plus 5 is the same thing as 5 plus 2. But when it comes to the difference, that order does matter. So it is very important that the sine first, cosine second is first in the difference. So if I remember that as being the first term for both, it just helps me memorize them. Similarly, down here with the cosine sum, so we have cosine of the first, cosine of the second, minus sine of the first, sine of the second. So for the cosines, we don't split up the trig functions, we actually keep them together. We put the cosines together and we write them first, and then the operation has been switched. So the sine sum is a sum, but the cosine sum is actually a difference. Alright, so if you can remember that the cosine sum is cosine cosine minus sine sine, then all you have to do for the difference is change these signs. So it's cosine cosine plus sine sine. Alright. The tangents, of course, they're quotients, and so they're a little bit rougher. But the tangent sum is a sum up top, and then you divide by 1 minus their product. The tangent difference is a difference up top, divided by the sum of 1 and their product. Alright, so in my in-class courses, I have my students memorize these. The best way to memorize them is probably just to write them down. So whenever you're working a problem in this homework, whether it's a verification or some sort of computation, if you use the cosine difference, write it down. If you use the tangent sum, write it down. Every time you use it, write it down. Don't just look at your reference sheet. Take it from the reference sheet and write it down. Okay. So memorize these the best you can. For my online students, you have access to these, but I still recommend you try to put these to memory. It's going to help with everything. It'll help with tonight's homework or this lecture's homework, but then moving forward with the double and half angle and future identities, we just need to have these memorized. And even throughout the calculus sequence and future courses. If you have these memorized, it helps just a ton. Okay. All right, so here we go. Let's actually use them. And there's several ways to use the sum and difference identities. One is going back to our friend, the unit circle. So if you remember, when we first started with the unit circle, we were able to find the cosine values and the sine values based off some geometry rules. It was the 45-45 and the 30-60 right triangle rules. That's where these values came from. And then we just kind of put them to memory. Well, the sum and difference angles can help us fill out a few more of the angles. In fact, these 15 degrees or these pi twelfths that we've been skipping over, we can now fill these in. They're not as pretty as these values we're more familiar with, but we can do it. So the pi twelfths, or the 15 degrees, the 75 degrees, these that we've been skipping. In fact, in our graphs, I would have us skip, dash, 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 skip, dash. Those values that we skip, the pi twelfths, we can find them using the sum and difference. Let's do an example. Let's find the exact value of cosine of, and I'll start off simple with degrees. Of course, we're trying to transition to radians, but I'm going to start off with something we're all familiar with, 75 degrees. So cosine of 75 degrees, this is asking if I were to draw a ray from the origin and intersect my unit circle, the point would be right here. I want to know the x value. That's the cosine value, the x value. So I can already tell you it's going to be smaller than a half, but I want to know the exact value. To find the exact value, we're going to use these sum and difference. So I look at cosine of 75. Well, that kind of clues me in that I'm not talking about sine, and I'm not talking about tangent. But I would like to somehow come up with 75 degrees, and the way we're going to do it is we're going to come up with angles we are comfortable with that either sum or differ to 75. So there's a lot of different ways we could sum or subtract our angles to get 75. I think the most obvious way would be to take 45 degrees and add it to 30 degrees. 45 plus 30 will give us the 75. So we're using the angles we are already comfortable with. That's the pi sixes, the pi fourths, and the pi thirds, all of those multiples. All right, so I claim our first step is just to rewrite 75 degrees as a sum or difference of two angles on the unit circle that we know the values of. So I'll have some students that try like a 60 plus 15. 60 plus 15, but we don't know 15. So that doesn't work for us. 60 plus 15 adds to 75, but we don't know the 15 value. So I like 45 and 30. So I'm going to rewrite this problem. I don't know cosine 75 just yet. I'm going to rewrite it as cosine of 45 degrees plus 30 degrees. Now all of a sudden I have a cosine sum. This is sum first angle being added to sum second angle. So I can use the cosine sum up here. And I just told you, whenever you're using these identities, it's probably smart to rewrite them. So I have it written right here, but I'm going to listen to my instructor. I'm going to write down this identity. So cosine of alpha plus beta is equal to, and I have it memorized, it's cosine, cosine, sine, sine, and the cosine sum is actually a difference. So it's cosine of the first angle times cosine of the second angle. The sum is actually a subtraction, and then it's sine of the first times sine of the second. Oh, I threw in the values. I guess that's probably smart. 45 degrees and 30 degrees. I was going to go through and write alphas and betas and then go through and substitute my alphas and betas. But I guess I'm comfortable enough that I say 45 and 30 is an alpha and beta, and so I can just apply the identity to look like this. Okay, Now this is so convenient because I know all of these values. I know cosine of 45 degrees, that's root 2 over 2. I know cosine of 30 degrees, that is, and if you need to double check your unit circle, the cosine is root 3 over 2, the x value. All right, so I'm going to say cosine of 75 degrees, or keep it as 45 plus 30. And then I know all of these values, they're just coming straight off the unit circle. Cosine of 45 degrees is root 2 over 2. That's being multiplied by cosine of 30 degrees. I had to look at my unit circle because I don't have it memorized in degrees, I have it memorized in radians. So 30 degrees is pi 6, cosine of pi 6 is root 3 over 2. From that I am subtracting. Sine of 45 is root 2 over 2. And sine of pi 6 is the lovely 1/2. Now we're just multiplying fractions. We just go straight across. Nice and easy. Root 2 times root 3 would be root 2 times 3, or root 6. 2 times 2 is 4. Down below, I've got root 2 over 4. They already have a common denominator, so I'm just going to put them together. And cosine of 75 degrees is equal to root 6 minus root 2 all over 4. That is the x value. That is the exact value of the x value sitting right here. Now it's not as pretty as the previous values, and I don't quite have room, but you could label it on your unit circle. But these values, no one expects you to have memorized. The 30s, 45s, and 60s, everyone expects you to have those values memorized moving forward. But a cosine of 75 degrees, they don't come up as often. So what we want is you to have the identities memorized and the ability to quickly come up with those values. Okay, so cosine 75 degrees is root 6 minus root 2 over 4. Memorize the identity and then be able to work through this process. Let's do that again. More practice. I'm going to switch away from degrees and go back to radians. But I'm going to keep this list handy. Oh, I do have it above me. Let's switch over to radians. I got an easy example in my notes. Let me make it harder. So I'm just looking at my unit circle, and I'm kind of pretending I'm a student right now. Let's say I want to find one of these gaps. So something like this. This would be 180 plus 15 degrees, or 195 degrees. How many radians would that be? Well, that would be 180 is 12 pi twelfths. So this is 13 pi twelfths. Let's find the sine value of 13 pi twelfths. Let me walk through that process one more time. When my students are preparing for an exam or an assignment, I tell them, there's only so many, I guess there's an infinite amount, but there's only so many values that I can ask you on a test if I'm trying to assess your ability here. So, go off and find cosine of 15 degrees, sine of 15 degrees, tangent of 15 degrees. If you've done that, then you're ready for that problem on the test. Go off and find cosine of 75, sine of 75, tangent of 75. If you've done that, then you're ready for that question on the exam. So I'm coming over here and I'm saying this is a good test question. What is the sine value of 13 pi twelfths, or 195 degrees? All right. So the first thing to do when you see this problem is just identify where that is on the unit circle. So 13 pi twelfths is sitting right here. It's 12 pi twelfths plus one more. So it's this little skip here. And if I'm asked for the sine value, then I want the y value. So I already know it should be negative in the end because I'm looking at a y value below the x-axis. Okay. And in fact, it should be smaller than negative 1/2. So, okay, great. I got a good estimation. But now I'm looking to rewrite 13 pi twelfths as the sum or difference of two angles that I'm more comfortable with. And if you need to convert this to degrees just to get those sums and differences, that's totally legal. So if you want to talk about this as 195 degrees, it may be simpler to find two angles in degrees on the unit circle that add to 13 pi twelfths. That's reasonable. So I'm thinking something big like 150 and 45. I'm able to do that in my head. 150 plus 45 would sum to 195. That means 5 pi 6 plus pi fourths, getting the common denominator, those would sum to 13 pi twelfths. So I think I'll just convert to degrees. That's simple. And then I'll use 150 and 45. So I'm going to spin a step to just rewrite my problem. I don't know 13 pi twelfths, but maybe I can handle sine of 150 degrees plus 45 degrees. That's step one. Rewrite as a sum or difference of two angles that are on the unit circle. Don't use 75. I mean, we just found it in the previous example, but those stick to the pi sixes and the pi fourths and the pi thirds. Those multiples. All right. Then I can apply the sine sum identity. Okay, this time I'm going to try to write it down with just alphas and betas. Sine of an angle plus a second angle, so sine of alpha plus beta. This one I have memorized as the two trig functions are being multiplied together, so it is a sine cosine. So it's sine of the first times cosine of the second. The operation stays the same, so it is also a sum. And then it's going to be cosine of the first, sine of the second. Just a little pattern to play with. Now that I have it written down, and it should be right above me, the sine sum is the very top one. Good. Then I can go forth and I can replace all my alphas with 150 and all my betas with 45. So sine 150 cosine times cosine of 45 plus cosine of 150 degrees times sine of 45. Yeah. So recopy it, get this embedded in your memory. Then I'm just substituting them in those values. And then I claim I know all the values on the right. 150 and 45 are on the unit circle, so I know these values. If I need to reference a unit circle, that's fine. But 150 is 5 pi 6, so the sine value better be 1/2. Cosine of 45, that's root 2 over 2. Plus cosine 150, now this is 5 pi 6, so it's negative, and that should be the root 3 over 2. I have my unit circle, I can just double check myself. Negative root 3 over 2. That's a 3. Negative root 3 over 2. Times sine of 45, which is that root 2 over 2. This is just multiplying fractions. I can handle this. Root 2 over 4. You're adding this negative, so you're just subtracting. Now this becomes root 6 over 4. And I can add these together. And I get root 2 minus root 6 all over 4. Now that was very similar to the one we just found. Just the placement of the minus sign, which I think I'm going to talk about in a second. But if my students stopped here, I would be very happy. This is sine of 13 pi twelfths. The exact value is root 2 minus root 6 over 4. That's the exact value. Now, I do want to talk about its similarity with that previous example. So I'm just going to play around with some manipulation. It is legal to factor a -1 from the numerator. I'm going to play around with that. So I'm going to pull a minus sign from the numerator. That's just going to change these values up top. So I have a now positive root 6 and a negative root 2, and I'm writing the positive one first. I did not change the 4 down below. I just factored a -1 from the numerator and kind of wrote it out front. Now hopefully you can now see what's going on here. That is the exact same value as cosine 75, except it is negative. You may ask yourself, well, why is that? And I claim that's because those are the same values. They are like cofunctions. So if I asked you what is cosine of 60 degrees and then sine of 30 degrees, that's that same value. So if I found the x value here at 75 degrees, and it was that root 6 minus root 2 over 4, but positive, and then I come down here and ask for that y value, notice it's that same distance. So the x value here would equal the x value here, which would equal the y value there, which equals the y value here, but negative. So it's that same distance. So, but we're just putting it in different quadrants, just like we did from before. We learned that cosine of 60 degrees is 1/2, and then we can just manipulate the signs to put them where they need to be. So that's one route. I don't want you to do this, but that's one route to finding the sine value of 13 pi/12 is to just find its equivalent in quadrant 1. So you could find the y value here at 15 degrees and then just make it negative. That is totally legal. You could do that. The idea, though, behind this homework is to come up with a sum or difference, apply the identity, use the values that are on the unit circle, and then find or simplify to find that exact value. Just know, though, that this is going to be the same value popping up over and over and over again. If I asked you for the cosine and the sine, those are the same values over and over again. If I ask you for the tangents, of course they're going to be popping up over and over again. It's just that the signs are going to be different. All right. Let's see. Yeah. Okay, so that's one way we use the sum and difference identities. We can flesh out that unit circle. We can now talk about the exact values of all those angles we've been kind of skipping over. The multiples of 15 degrees, or the multiples of pi/12. We can now handle. Let's talk about another thing we can do with these identities. I call these kind of fun problems. Let's find the exact value of something like cosine of 49 degrees times cosine 4 degrees plus sine of 49 degrees times sine of 4 degrees. Okay, well, I'm already scared when I see that 49 degrees. That's not on the unit circle, and there's no way I can take multiples of 30s and 45s and 60s and change that into 49. So no, that's not. I can't use those identities in that way to find cosine of 49. I'm not sure what that is. I don't have the tools yet to find that. But I do see some similarities. I see common angles, 49 degrees. I see the 4. Oh, and then I see the pattern. Cosine, cosine plus sine, sine. In fact, these two angles are matching. These two angles are matching. So we're just identifying that we're using this same sum and difference identity, but maybe in reverse. So I'm claiming we've got, there's a plus sign there, this thing going on. We have cosine, cosine plus sine, sine. So this is just the cosine difference, but instead of going from left to right, we're going from right to left. So let's make that switch. I claim this is equal to cosine of 49 degrees minus 4 degrees. The cosine sum is actually that cosine difference, or the cosine difference turns into that sum. This is just using that cosine identity. Let's see how to do this. This one right here. All right. And in this form, well, I can play around with what's inside the parentheses. 49 degrees minus 4 degrees is 45 degrees. Oh, this problem became super easy all of a sudden. This is just a positive root 2 over 2. That's the exact value of that craziness right there. I claim it's a fun problem, a little bit quicker, as long as you recognize those angles. Let's do that again, but maybe a little more challenging. Let's do cosine of 2 times cosine, let's turn that to a C, cosine of a negative 3 minus sine of negative 2 sine of 3. This is a C right there. So cosine of 2 cosine of negative 3 minus sine of negative 2 sine of 3. So there's no degree symbol here, so I'm assuming they're using radians, and these radians don't have that pi that we're like familiar with. So these angles are really, we're not familiar with this at all, but that's okay. I kind of see the pattern. I see a cosine cosine and a sine sine, similar to before, but the alphas are not matching. 2 and negative 2 are not the same angle. Negative 3 and 3 are not the same angle. Okay. Ooh, but there is some manipulation we can do with negative angles. Remember, cosine is an even function. So cosine of a negative angle is the same thing as cosine of that positive angle. I'm going to make that switch. I'm going to use an even ID just to rewrite that cosine negative angle as cosine 3. Similarly, sine of a negative angle, you can rewrite that as sine 2 as long as you make the sign negative. Sine is an odd function. I'm going to use an odd ID. You can kind of think of it as the negative kind of pulls out. Really, that sine of a negative angle is equal to negative sine of that angle. So I'm going to make that switch. I'm going to make 2 little changes to my problem. This is cosine 2 being multiplied now by cosine 3, even. And then I have a minus sign here, but I have a minus coming out, or kind of, I'm going to rewrite it. In fact, I'm not going to change the minus sign just yet. This minus sign I'm pulling down. And then if you have sine of a negative angle, you can rewrite that as a negative sine of the positive angle. Okay, now I'm going to acknowledge, yes, that's going to be a plus sign. You can maybe skip that step from now on, but I wanted to show it at least that one time. Now I have my alphas matching, I have my betas matching. It's a sum with the cosine cosine, so this must be that cosine difference again. Notice the sum, when I rewrite it, it's going to become a difference. So this will be cosine of 2 minus 3. I can handle that. That is equal to cosine of negative 1. And we have to stop there. Negative 1, in this regard, is some angle measure, some radian measure. So we are done. Now, if that were an inverse cosine, meaning the negative 1 is not an angle, but it's a ratio of side lengths, I know what cosine or arc cosine of negative 1 is. That's pi, but that's not what this question is. Don't get confused. This is not arc cosine of negative 1. This we know is pi. This is saying what angle does cosine map to negative 1? Pi does that. This is saying what is cosine of the angle -1? And we must be in radians because there's no degree symbol. It's just whatever that is. I could plug into a calculator if I needed a decimal approximation, but this is the exact value. All right, that's another way we can play around with these sum and difference identities. Using them in reverse, they become kind of just fun little, I don't know, just fun problems. Oh, and of course, because they are identities, the sum and difference identities, we can play around with verifications. Yay, everyone's favorite. All right, let's play around with a verification. Let's verify cosine of x minus pi halves equals cosine x times tangent x. So I just have this trigonometric identity I'm trying to verify. They claim it's true. It is true, but I need to verify it. So I'm going back to my skills here. I must justify my steps. In the previous problems, these are more just math problems. So it's very helpful if you write down your steps. I'm applying an ID, I'm multiplying, I subtract. That sort of thing is very helpful, and it's a good skill to use, but they're not necessarily required like they are required in a verification. Now all of a sudden, we're in formal math writing skills. I'm going to choose one side of the identity to manipulate, and I must justify everything I do. Okay, I'd like to verify this. If I played around to the right, I could see some like quotient identity I could maybe play with. Over here, you may see some familiarity with the, what's that called, a cofunction, but this is not cofunction. Cofunction specifically says 90 degrees minus the angle. So it looks like that. This is the angle minus 90 degrees. So I cannot use a cofunction identity here. But what can I do? Well, isn't this the difference of two angles? Aren't we talking about the difference of two different angles up here? This looks like a cosine difference. We've played around with this. I think I know the identity for this. The cosine difference is actually a sum. So I'm going to rewrite the left-hand side. This is a cosine alpha minus beta. I can rewrite that as cosine alpha times cosine beta plus sine alpha sine beta. That's going to be equal to the right-hand side of the equation. Notice the minus sign, all that does is it tells us which identity to use. Because we have a cosine difference, we rewrite it as cosine cosine plus sine sine. I have a lot of students, and I almost did it, put a minus sign right here because they see the minus sign in front of the pi halves, but no. This is just some alpha and some beta. It's being subtracted, so we apply this identity. But the alpha is x and the beta is pi halves. All right. I use the cosine difference identity. Now I know these values. A justification here would be maybe unit circle or just evaluate. It's a unit circle. But I know this. Cosine of pi halves is 0. Sine of pi halves is 1. Well, 0 times cosine, that's going to go away. That's just 0. And I have sine. I'm going to rewrite the right-hand side because I don't know how I'm going to get from there to there. So I'm just going to rewrite my right-hand side. And in this step, I just multiply. All right, now that's a little bit tricky because notice it was co-functioning. I have a lot of students that will accidentally call that a cofunction and say, oh, it looks cofunction, so cosine of that is sine. But that's not cofunction. It looks like it, but it's not. That is some cosine difference ID and some evaluation. Okay, now I need to turn sine into cosine times tangent. So it looks like I need some cosine talk. I can put cosine on the left-hand side as long as I do it legally. I'm going to multiply by cosine over cosine. I call this multiplying by a fancy 1. We're just multiplying by a form of 1, cosine over cosine. A fancy 1. Now I'm just trying to make it look like the right-hand side. So I'm just going to rewrite this. I'll put the cosine in the numerator kind of out front. I'll put the sine over the cosine just to help me visualize what's going on the left. Rewriting is fine as a justification. Really, I guess multiplication is commutative, so I'm just taking all those factors. I got 3 factors there, and I'm just kind of rearranging them. And then I just have a quotient ID and I'll be done. Quotient ID. Sine over cosine can be rewritten as tangent. All right, so looking at the homework, if you see these, sums and differences, it's kind of obvious what you're maybe supposed to do because we're in a sum and difference homework setting. So let me do one more example. I think I'm going to choose a hard one just to show you that even I struggle with these. But let's verify the cosine difference of x and y over the sine sum of x and y is equal to 1 plus tangent x tangent y over tan x plus tan y. Let me say that again. We have cosine of x minus y over sine of x plus y, and that's equal to 1 plus tan x tan y over tan x plus tan y. That almost looks like a tangent sum and difference, but the signs are the same, so it's not quite the same. The tangent sum and the tangent difference have opposite signs on the numerator and denominator. So this is some sort of combination. I got a cosine difference and a sine sum, and this is like a combination of the two. They're equal, and I need to verify. And as I was saying just before, if you're looking at this and you're in the sum and difference homework, you kind of know what to do. We just learned the cosine difference, so let's apply it. We just learned the sine sum, so let's apply it. I will tell my students in class, if you're studying for an exam or an upcoming major assignment, take these problems out of the homework. So print off the homework, cut out the verifications, and mix them up. And then, try to work that problem kind of at random. So you don't know where this problem came from. Was this in the sum or difference? Did it come from a future lecture, double and half angle? Is this supposed to be like a easy one? So try to treat it as random. But for a hint for this lecture, it's sum and difference, and I'm giving you these in the sum and difference homework. So I think we should start with the cosine difference and the sine sum. All right, cosine of x minus y. We've done this cosine a lot today. This is going to be cosine plus sine. So I have cosine x cosine y plus sine of the first, sine of the second. That's all being divided by the sine sum. Now the sine sum, that's going to separate the trig function. So it's sine of the first times cosine of the second. It is still a sum. And then I have sine of the second, cosine of the first. Is that exactly how I wrote it over there? Let's see. Sine sum. Oh, I do switch the cosine and sine. That's okay though. Okay, and that's supposed to equal all that stuff on the right-hand side. Now, how in the world am I going to get all that mess to be that tangent stuff? Well, that's kind of a hint. I need all that stuff to be tangents. And how do I get tangents? Well, those are, it's a quotient, it's sine over cosine. So all of these, when I see that tangent x, I see sine x over cosine x, sine y over cosine y. So if I just look at the numerator, I'm just focusing in on the numerator, I do see some common stuff. They are both sums. They are both binomials. So they are very similar to each other. In fact, the tangent x, tangent y, it's a sine x, sine y over some cosine stuff. Well, this is a sine x, sine y. I just need it to be over a cosine x, cosine y. If this were divided by cosine x, cosine y, I could rewrite it as tangent. Oh, let me do that again. If this very first term were being divided by itself, it would give me that 1. So if I had a cosine x, cosine y divided by itself, that would give me 1. Okay, I think I'm going to use a super duper fancy dancy 1 here. I claim I can multiply at least the numerator by 1 over cosine x, cosine y, and then my numerator will be exactly what I need it to be. Okay, let's see if you agree with me here. I'll get my purple pen out. I'm going to multiply by a fancy 1. The one that I want is 1 over cosine x, cosine y. That's what I want to multiply through by. Now to make this legal, I have to do it top and bottom. So I'm going to multiply by a really fancy 1. Anything divided by itself, it should be 1. So this is a very fancy 1 that I'm multiplying this by. All right. Yes. My justification here is I'm multiplying by a fancy 1. All right. So if you don't see it quite yet, maybe you'll see it as I multiply. I need to go through now and distribute my 1 over cosine x, cosine y to both of the terms in the numerator, and I need to multiply that by both the terms in the denominator. So I'm going to have cosine x, cosine y over the cosine x, cosine y. That's being added to a sine x, sine y over cosine x, cosine y. Still have this giant division bar. Do it again. Sine x cosine y over plus sine y cosine x over what I'm multiplying by the cosine x cosine y cosine x cosine y. distribute, and multiply. Now there's a whole bunch of quotient IDs I can start to do. Oh, and just some reduction. Cosine x divided by cosine x, these reduce to 1. Cosine y over cosine y, this reduces to 1. I'll do red, and I'll say reduce. Is there any more reduction? No. Oh, look here. I have cosine y over cosine y. That will divide or reduce to 1. And then, was that a sloppy y or a sloppy x? That is a sloppy x. So I can reduce these cosine x's. They will reduce to 1. So I have 4 reductions. Maybe I'll say times 4 just to help the reader know what's going on. And then I have sine x over cosine x. That's a tangent x. Sine y over cosine y. That's a tangent y. This is a tangent x, and this is a tangent y. So I have 4 quotient IDs going out there. Okay, that was a lot going on, but I think I can handle this. All of that reduces to 1. Sine x over cosine x is tangent of x. This will be tangent of y. All over. Those reduce, leaving me with a tangent of x plus a tangent of y. That's exactly what I have on the right-hand side of my equation. So I wanted to show this example. It's a good one where we needed stuff. We needed 1 over cosine x cosine y. So I just went through and I put it there. In order to get all these just sines and cosines to be tangents, I needed cosines in the denominator. So I just put them there. Just multiply through by a fancy-dancy 1. All right. In the classroom setting, I normally have y'all like bust into groups, work on problems together. But I think I have shown enough. So the sum and difference, one major use is to fill out the unit circle, all the multiples of pi 12s that we normally skip over. The fun problems, just using these identities in other ways, just recognizing the pattern and applying them. And then, of course, they're identities, so we have more verifications we can verify now using these identities. All right. Practice using the sum and difference identities. Write them down over and over again. Do the homework. You got this. If you have any questions, just let me know.